Nice. Okay. To answer the question, I is defined as the square root of minus 1. Therefore, I squared is equal to minus 1. So 1 over I, if you multiply it by I over I, that's equal to I over I squared equals I over minus 1. Okay, review for the exam that we're having today. Yeah, we'll have the exam on Monday. Gives you an extra large amount of time to study. So, yes, this is not a history class, but we started talking about history. I didn't talk about history as much as I usually do, believe it or not. So, quantum mechanics, the reason for that history, why it exists, is to help us appreciate how people got to this understanding and what it means. Right, if you understand the origin, you have an easier time understanding what it means, I think. So I'm sorry, I was trying to shovel in food after you left my office. We still got food in my teeth. So there are the two approaches, the Schrodinger approach. Schrodinger was impressed with the de Broglie ideas and said, we should be able to have a de Broglie wavelength for an electron. And then I think it was Peter Debye said, oh yeah, then there should be a wave equation, right? And so he sat down, he came up with the wave equation using energy methods. And so he got the Schrodinger equation, the wave equation, that gives us the wave function that carries all the information. And that comes from energy. It's, in physics, in first semester of physics, we learned two ways to do our dynamics problems. One was Newtonian dynamics. We used Newton's second law fundamentally. And one was Hamiltonian dynamics, where we were using energy. And that's the approach of the Schrodinger equation. So it basically says the energy equals the kinetic energy plus the potential energy. That's essentially the Schrodinger equation. Now, the other one that we have not focused on, is Heisenberg's approach. Heisenberg was frustrated with not being able to find the position of an electron. And so he said, okay, let's ignore what we can't find and let's just focus on what we can. And so he started basically making tables to categorize, we have this or this, this or this, and the different values that you could have for the electron. And then he brought it to an advisor, and the advisor sent it off to a mathematician. The mathematician said, oh yeah, this is just matrix math you're working with. And so that's the other approach. So those are two separate independent approaches that came up with the same outcomes. You can do your quantum physics problems using either the Heisenberg approach or the Schrodinger approach, and you get the same outcomes. In some cases, one is easier, in some cases, the other. Almost always, they start you with the Schrodinger, the wave function methods, wave equation, wave function. So the Schrodinger equation, here what I have the details. You see there's a little psi squared there. I don't know why it's there, but that's what that thing is, psi mod squared. The Schrodinger equation was developed by Erwin Schrodinger in response to the challenge by Peter Debye. So I was right in my memory there. Useful for finding the wave function, applies the Hamiltonian operator for total energy. So, these are things that I do expect you to know, right? They're not just, things that have been said. These are things that I could ask you about for the knowledge section. The nature of quantum mechanics is important, right? We make a lot of conclusions based on our quantum physics. And if you have a different point of view, you might have more or less faith in different things. So how you view quantum mechanics is an important aspect. And right now, as starting quantum mechanics students, you don't have really a lot of background to even judge between these. Obviously, I'm Orthodox. I'm teaching Orthodox because that's what most people believe. But the realist position is the one that feels comfortable, right? The one that says that if we knew everything perfectly, we could know exactly what's going on. If we know what its position is right now, we know exactly what its position was a split second ago. That's the realist position. But that's not the Orthodox position. I was reading something recently, I think it was on Quora on the website, people talk about random things. And somebody was talking about quantum mechanics, and they weren't right, but they were right about this aspect, and that is that the electron in quantum mechanics is being treated as a wave, not as a particle. That is, it doesn't have a location. It's spread out. So what you could say, the electron is filling the entire orbital that you see in chemistry, but it's not, that's its location, it's filling it. And it's got different percentages of presence in the different locations. So that's, the Orthodox position is that it's non-localized, it's spread out, and that nature is probabilistic. So the meaning of the wave function, important things to note, psi mod squared is the probability density. That's the probability per unit space. And psi mod squared dx, then, you multiply by that piece of space dx, that's the probability of being in the region from x to x plus dx. And so normalization comes directly from that. If I have a particle and I have the probability of it being in this region, if I add up the probabilities of being in all the regions, it has to come to 1. So the wave function needs to be something that can be normalized so that you can have the probability of finding, if you search everywhere, the probability of finding a particle needs to be 1. And of course, when I say search everywhere, perfectly efficient search. We're not, your detector just failed. We extract information from this wave function using operators. So remember, we had a question on the quiz about what it means to be a function of the operator. If it's a function of the operator, that means the operator acting on the function gives you a value, an observable, times the function. So in this relationship here, the A needs to be real. It needs to be something physical. These are observable. I say physical, maybe I should say physical. But it's an observable, something that you can actually measure, which is why it has to be real. We don't measure imaginary values. And you have to get back that same wave function. That's how we extract information from it. There are some other things that I didn't really say. It has to be square integrable. I don't even remember exactly the definition of that, which is why I didn't say anything. Our operators are the functions that we use to extract information from the wave function. And we've seen only a few actual real operators, and then we've done a bunch of pie in the sky operators just to test to see if they were linear. So these are the linear tests, the ones that you did on that homework, so you should be really comfortable with that. You should be able to, on the test, given an operator, say, is this a linear operator or is it not an operator? Or given an operator, you should be able to calculate, is this function a function of this operator? Eigenvalues are the names for the observables. So I think I did talk about that terminology. We'll talk about eigenstates and eigensystems coming up very soon. Okay, the red is what I tried to use to indicate equations that you would have on the test. So you won't have the normalization condition on the test. That's something you have to know, right? You have to know how to normalize, know that it's integral psi star psi dx over all available space. Likewise, the expectation value equation is something you have to know. You have to be able to, given a wave function and given an operator, be able to find the expectation value. And so you have integral over all space. Notice I don't have limits on my integrals, but it needs to be over all space. our first problem, what would have been coming up on Monday, we're going to limit ourselves to a box. So all space is going to be from 0 to A, right? So that's why the limits actually aren't there, because it's over all space, whatever all space means. Integral of psi star operator psi. Really, really important to have the operator sandwiched between psi star and psi, with the operator acting on psi, because when you have the operator acting on psi, then you get the eigenvalue times psi. You move the eigenvalue through, and you have psi star psi to give you the probability for your calculation. Because fundamentally, when you're doing the expectation value, what you're doing is you're integrating the value times the probability of that value over all space. Standard deviation formula, that will be on the test, right? Don't expect that number. Difficulty, it's not scaled by difficulty what's expected for you to be memorized. It's more scaled on using stuff versus fundamental stuff. So the fundamental stuff I give you, the using stuff is what I expect you to have. So here you have the Hamiltonian operator. So you asked about the Schrodinger equation. The Schrodinger equation is that the energy operator is equal to IH bar ddt. The energy operator acting on psi is equal to the Hamiltonian operator acting on psi. So I will give you the full-on Schrodinger equation, but just pointing out that this here combined with this is what we use to get the Schrodinger equation to begin with. I think the IH bar is correct. Actually, front cover of the textbook, IH bar ddt. Yep.
So you just combine. You said
yeah, because here's the fundamental Hamiltonian equation. The energy operator acting on psi is equal to the Hamiltonian operator acting on psi, which is more fundamentally energy operator psi is equal to the kinetic energy operator psi plus the potential energy operator psi. Or because of our operator eigenvalue relationships, that's saying total energy times psi is equal to kinetic energy times psi plus potential energy times psi. Factor out the psi's, you have total energy equals kinetic energy plus potential energy, and parentheses times psi equals 0. Well, not equals 0. I said total equals total energy minus kinetic minus potential, and parentheses times psi equals 0. So it really is just an energy balance equation. And once again, one thing we'll learn real soon, starting Monday, is how to split time out of the Schrodinger equation. We'll have the time-independent Schrodinger equation where, well, we'll get there. Okay, and I think this is the last slide. It's a short lecture because it's just review and then you ask me questions. The exam is 1/4 knowledge questions in value. There's probably about the same number of knowledge questions as there will be actual calculation questions. But it's 1/4 the value, and 3/4 of value is in the applications. And of course, in time, it's probably 10%, 90%. So you'll have 5 knowledge questions that are asking things, like, why did Schrodinger come up with this Schrodinger equation? Or, how can you tell if a function is a function of an operator? And then 75% would be small calculations, things like normalize this or find the expectation value of that. Things that will require calculation, there won't be the big, long, drawn-out problems. There'll be basically pieces so that you have time to do it. So yeah, I guess I have 5 and 5 of each. And so, yeah, the limit equations, calculus tables will be supplied. Operators are on this. The calculus. This is the calculus table that will be supplied. I think. I don't think you'll need anything else. If you think you need something else, ask. And if it's it's a reasonable calculus requirement, like I don't remember what the integral of this is, I probably will give you something to help you out. I don't want to leave you stranded on that. And so that's what will be supplied. Otherwise, you need to know how to use the operators, how to do the quantum. Because what if we really established in this first chapter, we've established why quantum mechanics and how we do calculations in quantum mechanics. We haven't done any real quantum mechanics yet. And so that's what we're looking for. So that's the entirety of my review for the exam. So now it's your turn. What questions do you have? What do we need to cover more? Or, God forbid, we can put everything.
So there weren't any calculations that we had to do that really required like integration by parts, right? That was taken care of by the Gaussian table for the most part, except for the derivations.
Yeah, we did a number of derivations
Right.
where there was integration by parts. And so you could have to do integration by parts.
Okay.
We'll go over finding B to satisfy the shortage.
That was a pretty drawn out problem.
Yeah. Is that potential for the, I guess it's always potential for the test.
Pieces of it would be potential. The entirety would not be. Come on, go away. Well, that's wonderful. I mean, it did go away eventually, but that's because the app crashed. Let's see if she comes back now. So you had asked about if you looked at the solution, wait, this is homework 3, right? It's from homework 2? The question you're asking?
I don't know that we had to do it. I think we did it in class, problem 1.9.
We
the potential energy part, I don't remember how
well,
to do that.
the one he's talking about specifically is a problem that I did in class that was also it's not a problem. It was a derivation of the textbook that had a bunch of steps missing that I did in class. And then it was a homework assignment.
Well, I was looking through the problems in the book. There's one that if it's a derivation.
So yeah, let me find where it is.
Yeah, it's on page 20, 1.9.
I think you're talking about finding.
Oh, okay. That's a different question than I thought you were asking. Okay. So for this here, we are given, and so I'm just going to do 1.9b, right? That's what you wanted?
Yeah.
Okay, so notice I wrote this different than the textbook did, just separating the time part from the position part. And so we're asked to find Okay, so there I've used nifty color coding so that we have things separated. The green is what I'm looking for, so that's why I put that as a different color than the other operators. And so all I really have to do here is to move this over here. So I have this equation, and then I will factor out the psi and I'll be done. So, but I need to do those derivatives before I can factor out the psi. And so I just need to do what is the derivative with respect to time of this. So I'm just going to do as separate calculations. So d psi dt means you bring down the derivative of this portion, well, the derivative of the exponent there. So that's minus alpha I, or minus I alpha, and then it's still psi, because you have the rest of the exponent stays the same. And similarly, d psi dx is equal to, so I'm doing the first derivative first, then I'll do the second derivative, doing them sequentially. It's the safest way to do your derivatives. I know you probably can do it in your head, but you might make mistakes if you do it in your head. So bring down the derivative of this exponent, is the derivative of that exponent is minus 2 alpha mx over h bar. So then the second derivative is going to be using the product rule. The first times the derivative of the second plus the derivative of the first times the second. Which I will just multiply through all the way and not try to collect terms. 4 alpha squared m squared x squared over h bar squared psi minus 2 alpha m over h bar psi. So now putting those into my Schrodinger equation, I have I h bar times minus alpha I alpha psi plus h bar squared over 2m times 4 alpha squared m squared x squared over h bar squared alpha m over h bar. And so now I just need to combine terms and factor out the psi. So the last step is going to be combining the terms. I times I is minus 1. There's a minus there, so that makes it plus 1. So I'm going to have h bar alpha times psi. I'm going to factor out the psi. Plus the first of the black terms with the red. I'll have the h bar squares cancel out. A 2 cancels, leaving 2 on top. Alpha squared, 1m cancels. Then the next term, the 2's cancel. The h bars have 1 cancel, so I'm left with h bar. And the m's cancel. And so h alpha minus h alpha, those subtract out, and there's my answer. Hopefully that's what I got when I did in class the first time. Good. You never know when you're working a problem, right? It's not like it's 2 steps. Okay, so you have the process?
Yeah.
Okay. Other questions?
What's the significance of the wave number?
The significance of the wave number. The wave number, we've only talked about it very briefly here, but the wave number is effectively telling you what the wavelength is.
Okay.
Right? K is what? 2 pi over lambda.
Mm-hmm.
And so if you know K, you know lambda. And so it's, instead of using frequency, that's what spectroscopers use for, what is it, IR spectroscopy often.
Oh, use the K?
Yeah.
Okay, that makes sense. So instead of having it's kind of a simple equation, having momentum equals h over lambda, so I was wondering why I introduced the K term.
Well, there are cases where it's simpler to use it.
Okay.
And so in physics, you often use what's simplest, and that's why they use it. I think it's, like I said, I think it's IR spectroscopy where it's heavily used.
Okay.
Other questions?
Yeah, so if you have a wave function with, like, on page 14, problem 1.4, it has 3 parts there.
Mm-hmm.
You just integrate this up really high.
Yeah, so in this case, right, this was a case where your particle really only exists from zero to b, right? Because psi is 0 everywhere outside of that. And so when you work with it, yes, you do it piecewise. Your integral from minus infinity to plus infinity becomes 0 integrated from minus infinity to 0. No one's going to write that. Plus the integral of the psi from 0 to a, going from 0 to a. Plus the integral going from a to b of the other side. And then plus integral of 0 from b out to infinity that no one's ever going to write. I say no one's ever going to write, I'll write it, but.
So the theory that you went over, the history, was just a couple like Heisenberg and Schrodinger, but you started all the way from black body radiation.
Yeah.
Would you expect us to know all the steps?
You should know, okay, so why is black body radiation an important part? Black body radiation is important because that was the first suggestion of quantization in our atoms.
Okay.
And so that's why it was there, and so you should know that. You should know that's important, the first suggestion of quantization.
And all of the people who are involved in that? Like
No.
Or just
I mean, the only name I even remember is Planck and Einstein.
Okay.
Yeah, the person who sent him the telegram, the person he had supper with that night, those are names I don't know.
Okay.
I mean, those are part of the story.
Okay.
But, no. I was going to say the person you sent the postcard to, the person you sent the postcard to is the one that sent the telegram. So, yeah.
I don't have any other questions. I think pretty.
Good. Good. You guys, well, obviously I didn't give you back your quizzes because they're still in my office. Did I post your quizzes on Moodle?
I don't think so.
Yeah, that's the reason when you came in, I was going to give it to you. I was like, wait, I might not have scanned these yet.
Yeah.
So
Nice to see.
I don't see any.
yeah, check and see if it's there on Moodle. If it's there on Moodle, I'll go give them to you right now. I just don't want to give them back and then not have the record. I got 120% on. Don't you remember? Not you guys who do that, but it's practice. If it comes to that, Jack's willing.
No, they're not up there.
They're not, okay. Yeah, so I will scan them when class is over, and if you want to come by in 10 minutes, I can give them to you. I probably scan them because, I try to do that, but